This conference will now be recorded.
Good evening. So we'll today discuss about microscope. And before that, actually, due to technical problem, I could not finish the uh, human eye part, the last part. What I'll do, I'll just recap a little bit, and then I'll go to today's topic. Okay. So let me share my screen. So we had actually discussed the structure of human eye and accommodation, power of accommodation, etc. We had already discussed. So I'll just recap only those part, the defect part. Okay, the defect parts like hypermetropia and myopia, because those are the topics where numerical problems comes from. Okay, yeah. So yes, so first is myopia. So we had discussed the structure part of the human eye. Now see, I'll just discuss myopia once again. Myopia means short-sightedness. So look, there are few reasons for myopia. I'll just first let me tell you the reasons for myopia first. And what is myopia? Let me tell you, because I feel that day we could not finish this. So myopia is actually short-sightedness. It is a vision defect in which a person can see nearby objects clearly, but cannot see the distant object clearly beyond a certain point. And that kind of defect is very much common for children. What are the possible reason for those? The possible reason actually, possible reasons are the eyeball gets elongated along its axis so that the distance between the lenses and the cornea becomes larger. What happens? So the eyeball gets elongated, gets elongated. So this is one reason. Gets elongated. And second reason is because of this, what happens? The distance between, see, because of this eyeball gets elongated, because of this elongation of the eyeball, what happens? The distance between the lens and the retina. See, this is the lens and this is the retina. This is the distance. This distance becomes very, very large. Okay, that's why, see, short-sightedness means that person cannot see the far off object or the objects very far. So look here, the parallel rays, they will be actually converged before the retina, much before the retina. And we know that this retina, inner wall of the retina has the optical, like light sensitive cells and the nerves which carry the light signal as an electrical signal to the brain, and that's how brain analyze the image formed over there, and it's like it automatically invert it. Generally by lens we will get inverted image, real inverted image, but brain will actually make it erect image, erected image. Okay, so anything you want to see, the image of that particular object has to be formed by our eye lens, and that image has to be formed at retina itself, retina, anywhere on the retina, otherwise we cannot see. Okay, otherwise we cannot see. Look this case. So this is the defect part. See, far off object, if you keep one anything, like you just draw a tree maybe, so person cannot see this tray over here because the image of that particular object is actually formed here, not in the retina. This is actually short-sightedness or myopia. So what is the second reason for that? The focal length of the eye lens becomes too short. See, the light is actually getting converged very near to the lens. That means focal length is actually too short. F is focal length is too short. Okay, so these are the two reasons. Okay, reasons. This F is too short. These are two reasons for the myopia. One is eye lens gets elongated, so the distance between the lens and the retina becomes larger. Okay, and if the focal length of the lens, eye lens, becomes too short, these are two possible reasons. So for the short sightedness and or myopia. So I hope you have understood what is the problem. Now we go to the doctor, and doctor suggests to take a glass. Okay, viewing, like adding lens spectacles, and the spectacles actually have particular type of lens, whether, like, it depends on your problem. The ophthalmologist will suggest a lens, and depending on your power. Okay, depending on your power in the sense, like, exactly, we'll discuss it, exactly that focal length, like the exactly the the lens, correcting lens has to have a focal length in such a way that the final image has to be created at the retina. As you see, this is the corrected lens. So in case of short sightedness, see, the light is converging much before the retina. So what you have to do, you have to somehow diverge little bit, and the so this is the normal eye, this is the normal eye, this is the defect eye, defective eye, and this is the corrected eye. Okay, so this is the vision of eye, corrected eye, and this is the normal eye. So look what happens in normal eye. See, their far point, this far point has come to near. Okay, that means what you need to do when you have the light rays from the very far object, you have to use a concave lens to correct this problem, this defect. Why? Because, see, your parallel rays, that means rays are coming from very far of object, and upon refracted by this particular lens, the concave lens, we know if we have a concave lens, and when parallel rays comes, what happens after refraction? Actually they will seem like they are diverging from a particular point, right? They will seem like they are diverging from the focus, right? So this here there will be a virtual object, virtual image formed, virtual image will be formed. So similarly, we have to choose a lens such that the virtual image created by this concave lens will be exactly at the near point from where the normal eye can see. Okay. So this is the normal vision of the defective. See defective. So this is the normal vision. This is the defective vision. So normal vision, what that person can see, they can see from here only. Beyond this, person cannot see. So what you have to do? See the objects which are far off. You have to use a concave lens to see those far off objects. And how it happens? This concave lens will produce a virtual image of those far off objects at this particular point from where the eye can actually see. Okay, I can see from here, right? From here, if rays goes from here, this can be seen. Okay, all right, I'll just clean everything and look this part. So the parallel rays are coming after refraction, they go like this. Okay, and thereby if you just retrace them back, they will produce a virtual image, and this virtual image is produced at the focus of this particular lens. This is concave lens. And so what you have to have, so the near point of the defective eye has to be has to be equal to the focal length of the correcting lens. Okay, correcting lens. So this is the fundamental point here. Okay, suppose it can see up to, like, it has like 5.60 centimeter. If it is given that 5.60 centimeter, then 60 centimeter has to be equal to the focal length of the correcting lens. Understand? So this correcting lens. So this is the fundamental point here. You have to remember that the concave lens has to create a virtual image at the point, like, from where normal eye can see. Okay, all right. So by doing that, we can we can correct this particular problem, short sightedness or myopia. Now we'll just see hypermetropia or long sightedness. What does this mean? This person cannot see the nearby object. Why? Because, see, this is a defective eye. Okay, image formed by defective eye. See, the image is not formed at the retina. It is actually going beyond the retina. Okay, here. That's why, as we know, anything, like any image, like any object you want to see, the image of that particular object has to be formed on the retina itself. Otherwise, you cannot see. So in this case, look what happens in this particular problem or defect. A person cannot see objects from nearby, like objects from nearby, okay, or normal near point. So normal near point is actually goes far. Okay, this is generally 25 centimeter normal near point, but some people cannot see things from 25 centimeter. Maybe they can see from 60 centimeter. Okay, this is their near point. 60 centimeter is near point. Then what you have to do? See, the rays are actually meeting at very far off, like beyond the retina. So what you should do? You should make them fall on the retina and meet on the retina, so that a real image will form on the retina. So for that you need to use another converging lens outside. That is the correcting lens over here. Look here. This is the correcting lens, and the procedure is the same. What you have to do? Suppose your this is the near point. Okay. from where you cannot see. So suppose this is the point, and if you just have to raise here after refraction, see this particular correcting lens will create again a virtual image at the point where it can see from. Okay, so this is up to this, suppose this is 25 centimeter, so beyond 25 centimeter it can see. So what you have to do, this object which is at 20 centimeter has to be pushed to beyond 25 centimeter, maybe some 40 centimeter here. Okay, that object has to be pushed here. Okay, so but object cannot be pushed. You can do one thing, you can create a virtual image of that particular object beyond 25 centimeter, and for that you need to use a convex lens. Okay, so this is how hypermetropia or long sightedness can be corrected. Okay, so Deepa, I have given a few questions on this in the quiz part. Obviously I'll take uh, some example when time permits. Okay, for today we're not going to take the example part of this, or maybe I'll just take one short example, just one example I'll take, and then I'll go to the next portion. So look here, if some person, okay, let me just tell you the problem. A person wears a glass. See, if some person wears a glass of focal length minus 2, oh sorry, having power, suppose power, having power minus 2.5 diopter. Okay, power. If some person is wearing a lens having minus power and that to 2.5 diopter, that means what kind of problem or defect it has, like that person has. So correcting lens is concave where, in myopia or short sightedness. So you can easily find out what is the problem from the power, like power, the sign of the power itself. So the question is the person farsightedness or like has farsightedness or nearsightedness? It is nearsightedness. Okay, because the power is minus, the like the glass he wears has minus power, and correcting lens we know for myopia, the correcting lens is concave lens having a negative power. Now you have to find out what is the far point of the person without glasses. So without glass, what will be the far point? Okay, so look here. So we know the far point of the defective eye is actually coming to near. Here, what you need to do for correcting lens, see, lens has to have focal length exactly equal to the far point far point of the eye without lens, without glass. Okay, so this is the focal length of the, so far point, if you want to find out, you have to just find out the focal length of the correcting lens, that's all. That will give you the far point. So see, the power is given as minus 2.5 diopter, 2.5 diopter, and we know power is actually reciprocal of the focal length. Okay, from here we can find out the focal length. Okay, since it is diopter, this diopter means per meter. Okay, so we'll do sometime 100 by 2.5, and this will come in centimeter. Okay, okay, so look here, this will go like this. So it will be 40 centimeter. So the person has far-sightedness, like near-sightedness or short-sightedness, and it has far point how much? 40 centimeter from the eye lens itself. Okay. So this was the question. So the kind of this type of questions will come, okay, in your exams, various exams. So I have given in the quiz as well as in the MCQ practice part, like this kind of questions I have given. Try to solve there. Okay. So now we'll go. So Deepa, do you understand this part? What are the defects and how defects are corrected? Like what is the principle of correction of the defects? I hope you have understood. Or if not, then please let me know. I'm asking you now. If you have any problem, you can ask me now. No problem, Deepa. Okay. Okay, then I'll just go to the next topic. Today's next topic is simple and compound microscope, and next day we'll finish with the discussion of telescope. Okay, astronomical telescope we'll discuss and then finish the chapter. So today we'll discuss microscope. So simple microscope, you might be knowing what is simple microscope. Okay, what is a simple microscope? A simple microscope a simple microscope is just a glass. Okay, microscope or a magnifying glass, actually it is some kind of glass magnifying glass is just a lens, actually just a lens of short focal length. Short focal length. Okay, and at the same time the lens has to be held close to eye. Okay, this is a simple microscope. Simple microscope or magnifying glass is just a lens of short focal length and held close to eye. So that is actually simple microscope. Now you might be thinking, what is the working principle? So working principle, generally in the exam there will be a descriptive question in the board that write down the working principle of compound microscope or simple microscope, like that. So I have learned what is the definition. I'll just erase this just to save some space. Now we'll see the working principle. Okay, so this working principle, I'll just divide this into two parts. One is when the final image is formed at the least distance of distinct vision. Okay, least, I'll just tell you one more point. Distance least distance of distinct vision means what? So what is this? This is the minimum distance. Okay, this is the minimum distance where like where if we place an object, okay, so at which the eye can see the object without any strain, but I can see it clearly and clearly and distinctly without any strain, of the eyes. So this is called least distance of distinct vision. So that is actually denoted by D and generally 25 centimeter for human eyes, normal human eyes. Okay, so what do you mean by least distance of distinct vision? The minimum distance at which if you keep an object you can see that very clearly and distinctly without much stress. If you just bring anything, any object below 25 centimeter, below 25 centimeter and try to look, you cannot, first of all you cannot see things very distinctly. That means you cannot separate out the very minor details, and also at the same time your eyes will be fatigued, they will be strained. Okay, they will be strained. Okay, so this strain will not be there at 25 centimeter. This is called the minimum distance of distinct vision. That means the minimum distance where if you keep an object you can see it clearly and distinctly without much strain on the eye. Okay, all right, so this is called distinct vision, least distance of distinct vision, and denoted by capital D, and this is generally 25 centimeter for normal human eye. Normal human eye. Okay, all right. Now what we are discussing, working principle, working principle of this microscope, simple microscope. When the object is created or object, like image of the object has been produced at D, image produced at D. So image at D. Okay, this is in short version I am just writing, short in the sense like this is the image at at the least distance of distinct vision, so that I am writing image at D. All right, so if we do that, what will happen? See, in simple microscope generally the object is kept between, object is between, object is between the optical center O and F, focal length. That means within the focal length. Okay, distance of focal length. Then what we know for convex lens? See, this is, suppose here is the focal length, focus is here, so the object is here. So there will be a magnified and erected image formed on the same side of the lens itself or on the same side of the object. Okay, and this will be a very magnified image. Okay, now, so what we have learned, the simple microscope means simply a lens having very short wavelength, and we have to place the lens very close to our eye. What is the working principle? When the the image is formed, when the image is formed at the least distance of distinct vision at that particular time, if you keep your object at the distance from the lens below the focal length or within focal length, between, that means with in between the focal length and the optical center, then what happens? There will be an erected and very much elongated image formed. This is the image formed. Okay. Now you have to see in this case whether it is microscope or telescope. The main point is the magnification, how much it can magnify. So that is much more important than anything else. Magnification. We have to find out what is magnification, and this magnification is generally angular magnification. Angular magnification. Magnification. Okay, anyway, so this is angular magnification. Let us see. We have to actually find out whatever instruments you have. You have to find out few things. Among them, magnification or magnifying power is most important. Okay, and look here. So this magnification, M is defined as what? M is defined as the ratio of the angle subtended by the image at the least distance of distinct vision to the to the angle subtended by the object at the least distance of distinct vision. I'll repeat. I'll write it. What is magnification? Okay, so anyway, I'm just going to denote this magnification also as M. So what do you mean by magnification? It is the ratio of angles, angle subtended by angle subtended by the image at the eye. Okay, at the eye, when the image is formed, when the image is formed at least distance of distinct vision. Distinct vision. And to the, so this is the upper part. So angle subtended by object, same thing. Subtended, I'll tell you, then you will understand again. Subtended by object at eye at the least distance of distinct vision. It might be a little bit boring, but I'll now explain from the figure. See what I'm telling? The magnification is the ratio of the angle subtended by image. Look, I have the image over here. So this is the image. Okay, this is the image. So it is subtending an angle at the eye. So eye and lens, they are kept very close to each other. So you may think that the angle made by the image, okay, to the lens, okay. See, look this thing. This is the angle. So this may be called as beta. Let us take that as beta. Okay. So this is, and divided by the angle subtended by the object. Look, this is the object when, So suppose the image has formed at D. This is at D. This this distance is D. Now this object also has to be taken as at D. So you just take a parallel ray over here. So this is kind of like OB is equal to IB. Length is same. Okay. So angle subtended by this particular, you can see this is the alpha. So this is alpha. I'll repeat the magnification. So magnification is defined as the ratio of the angle subtended by image at least distance of distinct vision and to the angle subtended by the object, angle subtended by the object at least distance of distinct vision. Okay, by doing that, look, I'll just clean everything. So I'll just write this alone. So this is, I'm getting beta by alpha. Now these angles are actually very, very small angles. Okay, if the aperture of this lens is very, very small, and if we are dealing with the parallel paraxial rays, then alpha and beta are very small, and I can write without any variation if alpha and beta are very small. Okay, so now we can just take from here, see what is tan beta and what is tan alpha. These are few points we will be writing now. Look, this is your C point. Okay, C. This is C. This is O, and this is B. So from OBC, this triangle I can write COB, that is the object distance, divided by, so perpendicular by base. Base is actually OC. Again from this triangle, look, this is the triangle. Object is making this angle. This is the triangle. From triangle, this one, CIB prime, okay, or B prime CI. So this, from this triangle, so what we can write as tan alpha. So tan alpha can be written as B prime I divided by IC. Okay. Now B prime I and OB, they are of same height. Look, this thing. These are parallel rays, right? This one. So this B prime I and BO or OB, whatever you say, OB and IB prime, they are equal in magnitude. So look here. Then if I just put OB here also, then OB will get cancelled. So I'll get IC by OC. So what are these? IC by OC. Let us see. So what we have got from this figure is magnification IC by OC. So this is the, see, look, IC means what? This distance. What is this distance we have taken? That the image has formed at least distance of distinct vision, and that too with a negative sign. I can do that. So I into C, that will be negative D. And what is OC? Look, this OC. OC actually the object distance. If you look, if I just say that as U, so this is U. The object distance, this is minus U actually. So this is minus U. Okay, I'll just repeat once again, Deepa, for you. Look, from here, I am writing magnification. Okay, magnification. How? I know magnification is the ratio of the angle subtended by the image. So image formed at the distinct, like least distance of the distinct vision. Look, this angle, triangle. IC and M. This particular triangle you can look this. Okay, so beta is this angle. This angle, the image is forming an angle or subtending an angle at the lens, and alpha is the object is subtending. This is the object is subtending, and see, this object is actually pushed to the d distance because we are taking that this ratio. When we take this ratio, both object and image has to be at the distance of least distance of distinct vision. So this is alpha. Now since these two are very small, I can write tan beta by tan alpha. Okay. Now tan beta from triangle, see big triangle, this one MIC. From this particular triangle, I can get the tan beta. That is, sorry, I'm sorry, that is not the big triangle. We'll just take this beta means we'll just take this OBC, this O, B and C. So from here I can find out lumbar is OB by base is actually OC, and tan alpha is similarly, this is IB prime over OC. Okay, I'm sorry, this is not OC, this is IC. Okay, so you look here, IB and OB will be same as I told you. This is OB, this is IB prime. So they are actually equal in height. So we can just strike them out, and finally we get IC by OC. What is IC here? IC is this distance. This is nothing but D minus D I have taken already, or D. And what is OC? OC is the object distance. So that is also with minus U. Okay. So D by U. So what we get finally, magnification here is so D by U. So this part we have got already. Now we know the lens's equation, 1 by V minus 1 by U is equal to 1 by F. Okay. So let us see from here what we can do. See, 1 by V we know. 1 by V, that is the minus D. And this I have to, okay. This is the thing. So what we get, 1 by U is equal to 1 by U is equal to, so okay, U also was minus, okay, U also was minus, so it will be actually eventually positive here. So U will be equal to 1 by F plus 1 by D. Now if we just multiply, if we multiply D both sides, look, D by U, then D by F plus 1. Okay, so what is D by U? D by U is nothing but magnification, so 1 plus D by F. Okay, this thing. Now look, this is the magnification. That means if you use a magnifying lens, any object can be seen as this much. See, if I H prime is the image, so H into this particular factor. This will be the magnification. So look here, if suppose D is already we know 25 centimeter. Okay, what is F? If we take F is equal to some 5 centimeter, then what we get from here is actually 6h. So h prime is equal to 6h. Generally it is like it is the case, so it will be 6 times if the focal length is same. Okay, sorry, if focal length is 5. So that's how in this case, look, the magnification we have got is 1 plus d by f. That means if your f is very short, magnification will be very large. Okay, very large. So that's why it is said here in the simple microscope, the focal length, simply a lens having very short focal length. Okay, so short focal length you have to have. All right. So with this, actually we finish microscope, simple microscope when object image at when image is formed at D. Okay. Now we'll go to another situation when the object is, see, when the object is uh, or eye is focused for very nearby object, then eyes will be sometimes getting strained. Okay. To avoid that strain, generally what we do, we focus anything at very far or infinity. So if we focus any object, if we focus our eyes for infinity, then our eyes will be relaxed. But for that case, for by a simple microscope, when the image is formed at infinity, what will be the magnification? Look, this is the case. See, a similar thing that our eye will be kept near the lens, and then we will see an object which is kept at the focus. If you want to see the object, sorry, image at the infinity, then you must have your object at the focal length. Okay, at the distance of focal length. Look here. So this is the object distance focal length, and image is here somewhere. Okay. So look, magnification as we have defined already, that is the angle subtended by image. Look, the image is actually subtending angle at the lens here. See, this is the image rays of the image. So they will see, this is the angle beta. Okay. So this is the angle beta. This angle beta, which is created by image. Okay, which is created by image. And alpha, what is the alpha? Alpha is this one. Suppose, see, if this is actually kept at the distance of distinct vision. Okay, so magnification is defined the ratio of the angle formed by image at the eye to the angle formed by the object at the eye when the object is situated at the least distance of distinct vision, not at the f. Okay, so we can find out, we can just draw this figure. Suppose the object is at the least distance d. Look, least distance of distinct vision, this is d. So from here we can find out. So look here, I can, since this alpha and beta are small angle, then I can write similarly beta means tan beta, or see other way, tan beta is beta, that's why I'm writing tan beta for small angle. Again, alpha, tan alpha means alpha itself. Okay, so tan beta and tan alpha, look here, from here what you get for tan beta. Tan beta is this one, look, see, h by f. Tan beta you get h by f, this one. Okay, this from this triangle. And tan alpha you get h by d. So h is goes off, then you get dy f. So in the previous case, what was the magnification? That was 1 plus dy f. Now you get, when the object is formed at infinity, you get, I'll write infinity, and this is d. Object is formed at d, so that time the magnification will be more. So this one factor is actually getting erased for, or missing for, image at infinity. So this is d by f alone. Okay, all right. I'll just tell you the working principle of this compound microscope, and then maybe I'll stop it after doing that. Next I will take the telescope. I'll take maybe 5 minutes extra. Let me tell you what are the uses of this simple microscope. Like watch makers, jeweler makers. They use a very simple. They use this simple microscope, and they will be holding near the eye, very close to the eye, so that they can see a magnified image of the watch parts or very fine designs of the jewelries for a jewelers. Okay, and sometimes we use this magnifying lens or simple microscope in the laboratories to see very tiny objects like vernier scales, etc. Okay, so these are the uses of the simple microscope. Now we'll go to the compound microscope. I'll tell you here there are two lenses here, as you can see, two lenses. Okay, one is actually kept near the object. This is AB, the object. This is the object. One is kept very near to the object. So this is called objective lens. This is called objective lens. Okay, which is kept near the object. And another one is actually another lens is kept near the eye from where you are viewing. So this is called eyepiece. Eyepiece. Okay, this is called eyepiece. So look here, small. So both of them are having actually short focal length. For magnification, you need short focal length. For both of them, focal length is short, and for objective lens, focal length is written as FO. For this eyepiece, focal length is denoted by FE. One more point is the aperture for the objective is very less, whereas the lens as well as the lens aperture of the eyepiece is large. Okay, you can see from this figure itself. Aperture means simply you just take the length itself. So this lens has lesser aperture than the eyepiece. This is objective. This is called eyepiece. Okay. Now what we do? What is the working principle? See, if we keep one object here, just little bit away from, suppose here is the focal length of this objective lens. You just keep little beyond that, then what will happen? So this objective lens will create a real and inverted and magnified image, which is A prime B prime over here. Okay, so this is the object. Now image is formed over here, and the distance between these two lenses are kept in such a way that the image formed by the objective lens is within the lens, like optical center and the focal length of the eyepiece. See, this is the focal length of the eyepiece. This is the FE here. So see, in between that the image has formed. So we know already, if we keep one object like between center and F. So if object you keep, okay, in between the optical center and focal length, what will happen? You will see a very large magnified and erected image of that. So see, this particular image which is produced by objective lens will be acting as an object for this eyepiece, which is held near the eye, and this image is formed in between the focal length and the optical center of the eyepiece. And for that, finally, the image of that AB will be formed here somewhere. A prime, see, this is A double prime and B double prime. This is the enlarged image you will be able to see. Enlarged image. Okay, and in fact it will be, yeah, so this is the image. Okay, Now if you want to, so this is the working principle, this is the fundamental point over here. So the image formed by the objective will be acting as the object which is placed in between the focal length and the optical center of the eyepiece, and that eyepiece will act as a simple microscope, and it will create an erected, since this is A prime is inverted, so the final image also will be inverted, okay, inverted and enlarged image you will get. Now if you want to discuss about the magnification, then look for this image. We know m is beta, that is the image formed angle, subtend an angle at the lens, and alpha, that is the object subtend an angle. So image is, see this one, this is the image here. So this is for actually least distance, when the image is formed at the least distance. Okay, image is formed at the least distance, d. So alpha will be actually, see this is the object, so it will be here somewhere, this is alpha. Okay, if that is alpha, look, we can write so we can just draw this figure, because so this is d, image has to be formed at the least distance of distinct vision. This is alpha, this is h. So from here you will get actually tan alpha. I'll write similarly, I'll write here tan beta and tan alpha, because the angles are very small. That is how I take. Okay, so tan alpha will be readily here h by d. And what about this thing? This is beta. Tan beta is given as, so tan beta will be given by see, you can look from here. So this is the u prime. Okay, so tan beta is this one. Okay, the tan beta is this one. So this is ue, this distance is ue, that means the object for the eyepiece. This is, and see this is the a prime b prime, a prime b prime, a prime b prime, or which I can write as h prime also. So I can write this tan beta as, okay, h prime by ue, and here I can write as h by d. Okay, h by d. Now one more point we have to see. So what we get from here is this. M is h prime by, so h prime into d divided by h into ue. Okay, we'll keep these two things. See, we know h by h prime. What is this h by h prime? This is the linear magnification produced by the objective lens, and this is d by ue. So we have already discussed d by u means what? D by u. Okay, we had already discussed from here actually. D by u, that is also magnification by simple microscope. So actually the optic, see this eyepiece will be acting as a simple microscope. So this is the thing. So in the compound microscope, what is happening in the compound microscope? The magnification by both the lenses will be multiplied like this. And like, see, if we just use the lenses formula, see me, how me comes? Me we know already, d by ue. This is me. Okay, so this can be written as, again, d by ue can be written as 1 plus d by f into e. This is for simple microscope that we have already discussed. Okay, and and sim and for m, only m objective. So for m objective, we know this will be given by, this will be given by v0 by u. This not is 0, this is actually object, this vo, objective, o for objective, this is also o, into 1 plus d by f. So this will give you the whole magnification. Sorry, this will be the whole magnification. Actually, MO is V0 by U0. Okay, not 0 O, UO. Okay, so if we try to find out what is this V0 by U0. Okay, I'm sorry, I'm always telling that V0 by U0. This is for objective, so oh, you can say VO UO. Look, VO UO. Okay, so from here also you can see. So VO and UO. What is VO and UO? This is actually given by L by minus FO. What is L? L is the length of the microscope tube or the distance between two lenses. This L is actually, see, look here. I have VO. VO means this is the distance. See, this is the distance. This is the VO. VO VO is actually the length of the microscope or the distance between the two lenses. The distance between the two lenses. Okay. So this will be actually okay. So nearly equal to L, and U0 will be nearly equal to FE. Okay. So finally what we'll get, so this is FO. This is FO. You look here. V0 and U0. U0 is this one. This is the UO. As the AB object is placed at the focus, then the objective, like, the image will be formed at infinity. So we just consider that the object is kept at UO, means minus FO at the focus. So from there, actually, finally what we will get, M is equal to minus L by FO into 1 plus D by FE. Okay. So this is the final magnification. Okay, when the image is formed at D, when the image is formed at D. Okay, we'll stop it here. Next day we'll just recap a little bit with when image will be formed at infinity, then the astronomical telescope will discuss. So this is the magnification, the whole. So what is L? L is the actually the length of the microscope tube, compound microscope tube, and FO object is a focal length of the objective, and this is the magnification. 1 plus D by FE is the magnification by the eyepiece. Okay, all right. So with this you can see that the magnification can be actually by this compound microscope. Magnification can be sometime 1000. That means if you have a objects of some like 1 centimeter of height, you can see that by microscope magnified by 1000. So the object you can see as 1000 centimeter. Okay, all right. So we'll stop it here. Deepa, if you have any doubt, you can ask me now. Okay, if you don't have, then I'll stop it here. Okay, bye for today.
Thank you.